like, are you staying for the weekend with him, or do you want to drive back with me?
I guess I need to drive back with you.
Okay, alright, then I'll take you guys back up here. Okay, sounds good. Alright, we got it, and then we'll just...
You will be driving.
Yes.
Thursday, right? Thursday?
Yeah, Thursday I'd be heading back.
He's also driving.
Yeah,
Is your better? You
we'll
want
take
to
the
fly
rest of the people, everyone is not.
Yeah.
Okay.
Okay.
Because I just can't take people down there, but I'll take people back up. Because I have to come back on Thursday. So that would work out.
Okay. So, yeah, I guess we don't know who's going. Did we figure that out just now? Like,
I mean,
who's
you guys could
driving
go
who?
together, and then Aaron can
3
go.
people, including you? Or
I think
I could fit 3 people in addition to me. It might get a little bit tight, like we would have to put, probably like carry-on type stuff
Okay.
in the middle seat in the back, but it wouldn't be like,
So I think I can go with you and come back, boys.
yeah, you whatever. Yeah, that works for me.
yeah.
So
I
Saturday.
really
and
am
Okay.
not opposed to whatever. We'll obviously figure it out and solidify it more later, but as long as we know that we're getting picked up in Boston
Right.
and we're driving down there. Okay, and so then we're just gonna book that airplane ticket.
Okay.
What's that?
We'll just book that plane ticket.
Yeah, I think so. Levi brought up a good point. We should disable cookies and track and all
Oh,
that stuff.
for sure. Yeah, I'm
I
gonna
don't know if
log
it's
out.
gonna matter.
I'm gonna log out on my Gmail because I think that's how they're tracking what I'm doing.
Yeah.
Yeah. Anyways, I'll do it and then I'll buy it tonight because I'm tired of having it hanging.
Are we
over
still
my
buying the same tickets then?
Yep, same
Yeah.
tickets.
Uh,
I think those are the best ones. Is Svetlana not coming today?
There is always chance, but it is very low.
Okay. Yeah, she wasn't in the office today. I didn't think so.
She was at the home office.
Mm.
Well, many thanks for being so self-organized. It is always nice to hear. Everyone did figure out how to travel?
Yes.
Excellent. That's-
Yeah, because Fatima,
Dude.
the plane ticket is on the email chain. Did you see that?
Yeah, I
Okay.
took a screenshot so you can at least find the
Solid.
flight
Just
numbers.
find that same flight.
Do we just want to try to do that all at once after group meeting today?
I don't have my laptop with me. If we go back to I could do it on my phone, I guess.
Yeah.
Okay, I'll email you then.
Okay.
Yeah, pretty much. Yeah, because I
They'll be
remember.
like the
Or I could just do it on your
And-
laptop
And email me
afterwards.
the
Yeah.
last couple.
So we can just do that, yeah.
You don't
We
even
get 2 windows open
I'll
at the
let
same
you
time.
No way!
So we do have 2 talks for today, and let me do a little disclaimer that seems self-evident, but often it is through routine is being forgotten. There is a disease of a freshman. So let me make a diagnosis. It is when you do research and you present part of it and forget about it. Forget about it, same as about exam. And when you do next presentation, you do it as start over. And third is start, no. Most of the projects that you are doing, it's year-long history. You accumulate more and more data and see best of them and best of your analysis. It's not like I passed the exam and I'm starting over. It's even if later you do a brief paper or brief presentation, it doesn't mean that you when I go to sleep, I wipe off my memory. No, you accumulate everything you do during the year or 2 years, at least since last your published paper. If you don't have published paper, then all your scientific life stays in your memory. Another little disclaimer. Is anyone who doesn't have a pen? I have a couple of sure. So the main idea is that when we listen to a speaker, we are who?
I don't.
Thank you.
More?
Check if it rates.
Oh my goodness, I got the fancy one.
Yeah, the lucky one. So the idea is that we are practicing life as a big collective brain, and we are helping the speaker to improve and get feedback for the future. And if we do the same for each other, we will be stronger than anyone in the world. At least stronger than all regional universities of our level. So the idea is that when you listen, you either stop the speaker and tell you're wrong because of this and this and improve, or if you are hesitant to say it, you just write. I didn't stop you, but you are wrong. You need to improve this and this. And when, as a speaker, you get back this writing, you're not like, oh, it's my enemy, I will burn this piece of paper. You are reading and carefully insert the comments back into your presentation, which you inherit and accumulate through several iterations next time. It's not like presented and forgot. No one will check. It's more like self-conscious community service. I don't care if you do or do not do, but it's really helpful. And if we all do it to each other, it will be much stronger. Just an idea. You do whatever you like, but it is helpful. So today there will be two talks, maybe of a little different lengths. The first one will be a little shorter by Daniel. And when do you return back from your trip?
The 8th.
Okay, so between 8th and Boston, Daniel will need to go through the exam, even if he doesn't realize it. It will be assessment by the department of his progress as a first-year graduate student, and he needs to show his best of the best that he did during the year. And today is a seed of this yearly report. So even if he is not fearing it, we all should fear of him and give him best feedback. So Daniel, floor is yours.
All right, cool. So I've been working with a two-dimensional thin film study of perovskites for a while. Usually in this case it's cesium lead iodide or cesium lead bromide, sorry. So this is one of two of my models when it will show up.
Well, it's not yet a model, it is you yourself.
I'm not a model.
Okay, it should come back to the image. Yes.
Yes. So this is one of my models right here. It's a thin film.
Wait, where are the goals?
Where are the goals?
Yes. How are you going to serve the community? Which discoveries are you going to make before you build the models? Where is the literature ready?
So the goal of the study is to look into its photovoltaic properties and be able to see if it facilitates charge transfer, has minimal charge, what's it called, trap states. Because trap states, they kind of slow down the charge recombination process. But
so you want faster charge recombination?
not necessarily faster recombination. Well, if you don't have any type of recombination and the electrons just keep coming out and you're able to separate them, is that kind of the goal? You know what I mean? Just charge separation.
Question. What is the difference between photovoltaic application and light emitting application?
You should have answered.
Yeah. So light emitting will basically the electron will keep recombining. Well, the charge carrier combination will come out of the conduction band and back into the valence band, and there won't be no charge separation. It will just be a endless cycle, and
What
that's
is the recycle methods?
huh?
You said recycle?
Oh, endless cycle.
Oh,
Yes. No, you're okay. That's my fault. So yes, we have that endless cycle. Then it should give off a light, and that's sort of how modern day lights work.
and how do you get the electron in conduction band?
How do you get the electron in the conduction band? You usually excite it, and that's energy that is required is usually known as a band gap. But yeah, these are my two models.
Wait. So what are you going? Just summarize boldly. Which discovery are you planning to do?
What discovery? Trying to see. Well, I guess the two models I have is a lead-rich surface compared to a cesium rich surface. So trying to see which one of the two would have the less amount of trap states, because having more trap states would hinder the photovoltaic process.
Okay. Well, not necessarily photovoltaic. Some good properties. So you want to remove trap states.
Yes.
And what are trap states? Did you already introduce them?
Well, trap states are part of the carrier recombination process, and well, electron goes through its ways, starts oscillating through the molecule, and well, instead of it finding its way towards the end, it finds itself stuck in a certain area of the molecule.
Okay. Maybe not perfect, but in the right direction. Good. Okay, so you want to address this goal, to minimize presence of trap states. And in order to address this goal, you build some models.
Yeah. Okay.
Okay, go forward. Which models are you building?
So I have two models, a lead-rich surface and a cesium-rich surface.
Of which material?
Cesium lead bromide, perovskite.
It should be separate slide. Okay.
Three separate slides. Okay, no problem. So yeah, essentially this is what my model looks like. Up down with the, I have it laid down to the side to show the interaction of the surface. This is my cesium-rich surface. So you see that the lighter blue color, it's kind of the same color as those. I should have changed them, but so those are our cesiums. The reds are bromides, and then the yellows are our leads. The two molecules that I'm using is acetate and ethylamine.
What is the difference of first peak and second bottom peak?
This one, these two,
Mhm.
it's the same thing. They're just laying down. I don't know whether you can see the surface from a top-down view or from that side of view, but it's the same. It's just a different angle.
What is the title of the slide?
What's the title of the slide?
Yeah.
It's my cesium iodide one. I didn't include the title.
So dimension is not an issue here.
Excuse me?
I mean, dimension is not an issue here, right?
Dimension.
I mean, X, Y, Z directions, anything is this a parameter or is it important or not?
Yes, it's of course it's important. I just didn't show it.
Explain if you can just index by finger.
Oh, so the top down is this the axis.
Mm-hmm.
Left to right is my x-axis. Then that into the plane of the board is my y-axis.
So you're working on
How much vacuum do you have?
How much vacuum do I have? On which coordinate? I guess.
It's periodic boundary conditions, right?
Yeah.
So I would assume if you're doing a thin film, you only have vacuum on one side. If you have vacuum on two sides, then it's not a thin film.
Yes, I have a vacuum.
So is it thin film?
Yeah.
Oh, okay.
Yeah, my vacuum is about 15 angstroms, if I remember.
So is that 15 angstroms on both sides or a total?
Just on the z-axis.
Yeah, but you have top and bottom of the thin film. So if you have 15 on top and 15 on bottom, then your vacuum is total 30.
Total 30.
15 in each side or total 15? You
Just a total 15, I think. Yeah, I think so.
What is the thickness of your unit cell? I mean your field.
Thickness. So, what do you mean by thickness?
This is a 2D film, right?
Yeah.
So what is the thickness of this film, your film? Because it's confined in one-dimensional confinement.
Mm-hmm.
So what is the thick length of that confinement?
Thick length of that confinement.
I mean, this is 2D films. It's important parameter.
Yeah. Guess I wouldn't really know how to even begin with that answer. Yeah, or how to find it.
What's the size of the unit cell for cesium lead bromide?
Size of the unit cell?
Yes. What is the distance between nearest sky blue atoms on your model?
Oh, from blue atom to
Yes.
blue atom?
Yeah.
About 6 or so.
Okay, and then you can just count how many of these unit cells is and scale and tell what is the size of the cell.
Like 30? I don't.
How many layers here?
Excuse me?
How many layers does it have?
How many layers? It's 3 layers.
So
Do you-
3 times 6 equals
18.
good.
Wait,
And
how
what
is
is this?
it 3 if there's 4 of the light blue dots?
4 of the white of the dots.
3.5.
Because like I see it very distinctly like 4 layers.
It's 3 layers. For the fact that if we lay it on the side, see.
Can
See
you point the layers out?
Yeah, layer right there. It's not exactly like lines throughout it like that. They're some are a little in the back, so the view of plane might be out of context. It's more of a, it's kind of hard to be able to observe it on the screen. But yeah, there's 1 layer right there, 2nd layer right there, then my 3rd layer right there.
Wait, which way
I
are the
feel
layers
like you've
going?
got half a layer that's like an extra half.
So if you look at your top model, it's like,
If it's like the two
Is it
like
both the same?
layers.
right, but it's easy to see on the top. So like lowest 3 dots
So like a layer should be like this.
would be like
Yeah, yeah. There's
the thin film part. And the top layer would be the
So he's looking
surface,
at like
right?
what happens if you have like
Hey Alexa,
whatever, and then so like
Yeah.
you're gonna kind of always have like that extra half
Okay,
there.
alright. No, I got it. I'm good. I'm good.
okay, because the reason why if you look at the top left figure, you only have, you don't have the blue on the other side is because half of the blue atoms on the left can be on the right because it's periodic boundary conditions. Right?
Oh no, I was thinking more top to bottom, I guess, instead
Oh,
of
okay.
left to right. But it's fine. We can move on.
Okay, so you did build a model. Oh, this is too bad.
So you say you are starting in selenium rich or something?
Cesium.
Cesium
Yes.
rich. So how this surface become rich of cesium? I mean, what is the more?
Well, it's probably a good idea to separate it. But anyways, so at the surfaces where the ligands are attaching to the surface is an abundance of cesium compared to lead. So I have another model where the leads are high in concentration on the surface compared to cesium. So it'll be more like I sliced off a layer.
I guess you remember you presented a general club presentation on the surface layer.
Yeah.
If you use those kind of images, it will be better to understand how it's moving.
What is those kind of images? Yeah, I'll look into that again. Okay.
So are your ligands charged or are they neutral?
They're charged.
Okay.
Explain more how are they charged.
How are they charged? So the acetate ion is negatively charged, while the ethylamine is positively charged, and combine both of these, and sort of they'll make a PN semiconductor on the perovskite surface.
This is conclusion that may or may not be supported by the data.
Well,
But-
so far from what I've done yet.
From your previous attempt, it is only one or pair of the ligands. If there are a complete layer of ligands, it may not be true.
Might not be true. Okay.
So, I'm assuming this is like to your committee, right? Or no? This presentation? It may be good to have not the actual system, but a schematic diagram, because I either missed it or I can't really see that there's two different types of ligands on the surface, and a schematic diagram tends to be very easy to perceive. So you can have like a chunk of your perovskite and then have ChemDraw and draw different ligands so that it's abundantly clear what's going on.
Yeah,
Does
you
that make
presented a
sense?
similar paper last week, maybe a week before that.
About
You
what?
you presented a paper on perovskite, and they're showing that they're showing how 2D layer is become iodine rich or something rich in them like that. So you use that kind of image. That would be more understandable.
Okay. Yeah.
So committee members are like babies. You need to start from very beginning.
Okay.
They can be of higher like academic rank, but not everyone in the world deals with perovskites and this ethyl ammonium ligands. You need to start like you do for freshmen.
Okay.
And then you can ramp up and go for complicated material, but start should be always for general audience.
Okay.
Okay.
And another question, is there a reason why you have your system upright and then turned like 80 degrees down?
No, he just said it's just showing us. Yeah.
Just to be able to point out the surface of the cesium rich, I guess, because I didn't think a top-down view would be
Oh,
all
okay.
all that helpful, just in case if I needed a second image.
So the capping ligands are different for the top and the bottom. Why is that?
The what?
First, yes. First answer yes or no.
Is that ligand difference top and bottom or same?
They're the same.
The same?
Yeah.
Is there a number of ligands is different on the top and bottom? How many ligands are on the top and how many ligands are on bottom?
Is 6 or
He's counting himself.
There's 4 of each ligand. So I got
On
4.
the top and 4 of each on the bottom.
Yeah. Well, it's 4 of both ligands on top and bottom.
Okay. And this layers of each layer of ligand on top and bottom has total 0 charge, right?
Yeah, it should. It will be total 0 charge, I guess. Yeah. So the system won't be charged. They sort of would cancel each other out.
It will be or
How many?
is?
It won't.
It
it's-
won't be?
They all have a. It's all equal to each other, so they might have a -1 charge, but this one has a +1 charge, and they're in equal proportion to each other.
So
How
then
m-
it doesn't have a charge. Okay.
How many atoms on the surface of this perovskite layer? Because I'm just wondering how you place the ligand, how is coordinated with the surface.
How many atoms are on the surface?
I mean, how did you? What do you think when you placing this ligand atom? You just randomly placed or?
Oh, the ligands?
Mhm.
Yeah, I just randomly attacked it. Well, normally I coordinated where the charge would be at, pointing towards the surface instead of just like flipping
Pointing
this
towards
back around.
which atom?
Huh?
Which atom on the surface? Because there are 2 types of atom on the surface.
Yeah,
maybe.
Great question. It's very relevant and yeah.
Okay, so I tried to apply the acetate ion more to the metals in my compounds, so such as cesium or lead. In this case, it's a cesium-rich surface, so I'll be trying to place it on my cesiums, and then the ethyl ammoniums would be on the bromine.
Great words.
So
You need to put it in a separate
then,
file.
Okay.
There are a lot of things on your model here, right?
Yeah, I gotta. Yeah, there's a lot of things.
We need to know what is your model and detail everything about your model. I have one silly question. So now, why your homologous is negative here?
So I think I just took the conduction band minus the valence band, and I call that the homo-lumo gap.
It's either a hyphen or
What's
he
the
was
value? I can't see.
trying to put a smile symbol. Column dash and then closing bracket.
No, it will become surprise model, column dash O.
What's the value? It's hard to see in the screen.
The
Is
value of
it
the
negative
homo-lumo
0 point? Yeah.
gap? 0.9.
You will found the slide in the email, just check the email, yeah.
It can't be 0.9 with that DOS because unless you have
It's
a
more,
state
it's more
that
than one, yeah.
What you
it
did,
has to be more than one.
you subtracted the wrong way. You should have done it the other way around.
The other way around.
Can you graphically tell what is the gap based on your density of states?
Yeah. It should have been that.
So like,
instead of subtraction.
Just approach and finger
Minus
which
negative.
two numbers should you subtract.
When he subtract, he forget to
numbers
put
right
the
here.
minus.
So what's the distance from these 2 points on the x scale?
what was the
From minus 1.5 to plus 0.5.
2?
So what's the gap?
2.
Good.
Because I guess.
Yeah, you
I see what I did.
positive,
He
minus,
forget to
negative.
put the minus sign, so it's
Yeah.
plus and it's become negative.
I actually, what I also how I got this value is that's the those are the eigenvalues I used there instead of that. So that's the
I can go lower.
eigenvalues of the orbitals of the homo and lumo gap. I think I
So that should
Still
give that.
that doesn't.
Yeah,
It
that's
shows
fine.
like either minus 1.5 or plus 0.5.
yeah.
What you did here, you did the minus 1 point something. Instead of minus, you just plus the other one.
Oh, I see what you mean. Now I
That's
get
why
it.
you got
Yeah.
this number.
Okay, that makes sense. Okay. Yeah. So yeah, I think if it was like 1.5 and then 0.5 and then that's what I got. Okay.
This is the sum of homo energy and lumo energy. not-
Okay. I see what you mean. Yes.
When you present this, you like remember in class we had the intense argument about whether or not it should be centered at 0. Do you remember that?
Center to 0. Yeah.
Yeah. I think that in order to avoid that conflict, you should do that for this.
Should do what?
So center the homo-lumo gap at 0. And then state that. Because otherwise, like, people like Svetlana are gonna get really upset that it's not centered at
No,
0.
in VASP, there we can center on the Fermi energy. Maybe it's Fermi energy. I don't know how it's going to work.
If you subtract the same number from energy of each orbital, just shift the x-axis, then you can find such shift parameters that the 0 will be exactly between homo and lumo.
Let's shift it.
You can. You can even change, like draw new numbers in PowerPoint.
Because the energy is
Redefine the labels.
doesn't matter. All that matters is the gap and the peaks
That's
and
right.
stuff.
That's right.
Yeah.
So
Because he did not able to start talking about the grainy graph yet, I guess. He did not start talking about any graph yet. I guess
I haven't even started.
give
Like, you
him
guys just
floor
keep
to
asking
talk about,
questions.
yeah.
Yeah. But yeah, that's a good point out. So I still don't get why this should be close to 0, but or why it should be centered to 0. I do remember that
Because it's
that-
the
that's
center.
discussion. The
So
center.
then it's so easy to see the difference between the homo and lumo then.
Oh, so like
It's just like a visual pleasing thing.
visual pleasing thing. Okay. All right. Yeah. I'll try to fix that up and see. I'll play with it.
Okay.
I'll see if I can make that happen.
Okay,
Shouldn't be
now
too
we'll
hard.
start talking about that one.
So so my other surface, the same mistake for the homo-lumo gap, but it's good to know I learned from that. So but anyway, so here I have the absorption spectrum from this.
Did you finish the task already?
No, I haven't even talked about it. I thought you guys already destroyed. But yeah, so the homo-lumo gap was around 2 eV volts, and so for the most part, all the electrons are usually found in the valence band, or no, in the conduction band. I apologize. No, valence band.
So what is the other significance of the shape of this unoccupied and occupied orbital gap?
So what is the difference between?
What is the significance of the shape of this occupied orbital being an unoccupied orbital?
It's more intense than the unoccupied. So I guess it's more likely to be found in the valence band, or
Did you look at the projected density of states?
no.
That might be important because I think Jabez asking like a physical what is going on, and a lot of times in like quantum dots, the valence band is the non-metals and the conduction band is the metals, and you can talk about the electronic properties looking at the DOS if you have the projected density of states. Does that make sense?
Oh yeah. Now I understand why everybody shows the PDOS on the papers now. Yeah, that makes sense now. Thank you, Levi.
And another things, look on this DOS. You plotted almost everything on the occupied. Then have unoccupied. It just started and you finished the. You should plot a little more energy.
I mean, I tried to make it bigger. It just wouldn't happen. So, but I'll work on that. Yeah, I see what you mean. I was
You
trying.
didn't understand how this script worked. That's why.
Yeah, I didn't. But yeah, I understand. So yeah, so sorry, my density states is lacking. Yes.
How did you identify trap states if you don't have the projected density of states?
How?
Yeah.
Through the orbitals.
Okay.
And that'll happen after this live.
Okay.
So yeah, so I have an absorbance. I calculate the absorbance spectra, and usually you see more of the excitation peaks to be around closer to UV range than the IR range. So more optically active in the lower wavelength.
Can you find online absorption spectra of perovskite thin films and put them nearby for comparison?
To do what?
How do experimental absorption spectra of perovskite thin films look like?
How do they? Okay.
You know how to find it?
Yeah.
You do not need to read papers. Don't waste time. Just go to Google, type perovskite absorption, search for images,
Okay.
and it will pop up immediately.
Okay.
And then you can tell whether whatever you compute is realistic or not much.
Mm-hmm. All right. Yeah. And I already know I'm getting chewed out for this one, but so this one is using the transition energy as the x-axis, compare that to absorption, and I don't know how to. Yeah, I don't know how well to explain transition. Oh, won't go back.
Escape.
Yeah. So can I know how to move that camera?
I have a question. It's not a scientific question.
Okay.
Just wondering, what is the spectrum U113?
Wanted to be.
Why you didn't change the legend here?
Wrong question. Do you know how to change the label?
What'd you ask again?
The legend of these all graphs.
Okay. So the absorption
It should be
spectrum?
informative. Yeah. Why you are just a spectrum Q?
Why?
How to change the legend?
Oh,
How
change the
to
title.
change the words spectrum U1:3
I
to like my
I
best.
see what you mean. I haven't got the slightest idea in the world how to do that. I forget that it's up there sometimes. I think.
No, I am asking because you are going to present in the formal committee meeting. That's why I'm just giving you.
No, I think I'm just gonna probably throw like a little white box over it and cover it. You know, like white out on the computer.
Sure.
Well, then you need to put a
You
title
can
in.
Then I need to put the title. Sure.
you can remove the legend. I forget what it is in GNU plot, but then it won't have any key. If you don't want to figure out how to change it, it's one line command?
It's not line, it's just a couple of symbols. Instead of in between using columns 1, 3, and then next keyword with line, you put TT, and then in the apostrophes in between primes you put like nothing or your preferred word that you want to show up.
What is this all keyword, man?
It means title.
I used only Fortran and
Oh,
Google
that's all.
for my degree.
Oh.
So yeah, I don't really know how to explain transition energy. If I could get some help on that, I'd appreciate that. Yeah, I included it up there, but I don't really know how to read one of those yet.
How do you get the absorption spectra then?
I know they're both linear to each other. I just don't know how to read a transition energy, but it's probably the same way, right? If you just
Look on these two figures, then you will figure out the difference.
I mean, it's the same exact peaks, kind of just flipped around.
Why?
Why? Because I guess wavelengths. Well, no, wavelength means energy, and I guess that's what it means, right?
What is the connection between wavelengths and energy?
Isn't it the lower the wavelength, the less the energy? Or
That's,
more the-
that's correct, but can you write it as a equation? What is the proportionality coefficient?
What is the proportionality coefficient?
I remember I told you once. Maybe you forgot.
You did tell me once. I probably forgot.
Okay, then do not bother. Just
Okay, then
put in a box. Ask Javed.
Yeah, Javid like mine. Yeah. So I guess that's what it sort of means. Is just with the wavelengths converted to energy, then. Okay. All right.
Right.
Good enough. So here's a couple of interesting models that I decided to show.
What else? It's only
models.
one model.
One model, many orbitals. There you go. Yes.
Sorry, back on your other thing. I think it would be more helpful if you included like the absorption spectra for like, I don't know if you guys said it, I kind of zoned out for a second. But if you included one for like something that's not this model, did you guys talk about that? Like include it for one without ligands on it.
One
Just
without the
see what
ligands.
happens when you add ligands.
Okay. Yeah, I think when I do my committee meeting, I'm gonna have to go from the beginning, so I do have that information ready.
Okay, because like this doesn't really tell you much right now. I mean, like it does, but not.
Nothing
You
to
know,
compare with.
you know what
Yeah,
I'm
yeah.
saying. Okay.
Hey, another question. Do you know how to get the oscillator strength from Conchon orbitals? Or the formalism for it? Because I'm pretty sure if Slavana's on your committee, she will ask that.
Note down
Yes,
these
you
all
will.
questions. You will get this most question in the group, in the committee meeting. Committee meeting is exam, so note down those questions.
Yeah.
It's better to find out the answer after the meeting.
Yeah, there's a recording of this. I'll probably
Oh, okay.
look at it a lot.
I may try to protect you on the committee meeting, but not against any question. So you need to prepare well.
Very well. Okay. Yeah. And no, Levi, I do not know what
Okay, I guess
says.
you don't need to answer right now. Maybe you can just note down the question.
Yeah, just listen to all recordings and read whatever we are writing.
Okay. Yeah.
Maybe just include a methodology slide
Methodology slide. Yeah.
with equations, because it is your favorite.
Yeah. Of course. So yeah. Here are a certain amount of transitions. I included these because they're the most optically active compared to the other ones.
Which one is HOMO and which orbital is LUMO here?
Which one is
Convection and-
HOMO and which is LUMO? I didn't include the HOMO and LUMO.
You did include LUMO, but you have hidden HOMO from us.
I didn't HOMO from you.
Is there something special about the two on the left? Like, is there a reason that they have like the bold box around them, or is that just an artifact of how they
No,
got
I
copied
guess
in?
How he took the snapshot at that time.
Uh-huh.
Maybe his HOMO was 412 and everything in box is occupied. Or you,
Okay.
I think so. I wouldn't want to say no, but yeah, I guess that's something I have to look into again.
And I guess I have a follow-up question too. You said that these are the most optically active.
Well, some interesting ones to look at.
Why?
Yeah. How do you know that these are more or less optically active than anything else?
Due to their high oscillator strength, so it's just a higher probability of that transition happening.
Okay.
Oscillation is
why don't you show the slide with a table of oscillator strengths and tell which one contribute more to?
I didn't include the table.
But you could.
I could, yes, of course. That probably would have been helpful. I should have looked into that. Instead of just you guys have a look forward. But yeah, you had something to add or no?
No, I mean, you said you are interested because of those give you the bright transition.
Yeah.
But transition to which orbital to which orbital? Because there were 4, 2.
Okay, I see what you mean. Yeah, some of these are pretty high. They usually went from like 412, 411 to like 476. They're pretty substantial
Okay.
changes. Yeah, and I guess that's something nice to include as well. Okay. Yes, Elizabeth?
I just for the what's the difference between like an optically active, like what are you looking for that's different from an optically active like perovskite versus a photovoltaic? I don't really know. I've never worked with it. Like I don't understand what the difference is between what you're looking for.
So what is optically active? So when it's optically active, it means it'll have a high absorption.
So why are you looking for optically active for a photovoltaic?
Why am I looking for it?
Yeah.
Because those certain transitions, they will emit light. Light is
Wait. Photovoltaic, you are not emitting light. Again, please repeat a question that you have already answered. What is the difference between photovoltaic application and light emitting application?
what is the difference? Whether you separate the charge or not?
Assume that you are delivering a lecture to freshmen.
Okay.
You cannot give short sentences. Answer in full.
Explain it to me. I'm the perfect person to try to explain it to.
So it basically, whenever you shine a light on the material, you excite the material. An electron will get excited and travel from the valence band to the conduction band. And when it's time for the conduction band, it naturally, it'll want to go back to where it started because it's like it went to the market and then it just wants to come back home.
Okay.
So in that process, you kind of want it to get lost for photovoltaic properties because if you could separate the charge, you could have and you could produce energy.
How is it related with the absorptions? You answered, but not directly, I guess. Yeah. I mean, for photovoltaic application, you need the electron and the conduction band.
Yeah.
How you bring that electron there?
How I bring the electron there? You
could
excite it with a light.
That's a hard question.
It's the first part of a process. But after photoexcitation, let me answer because I'm tired too. So if it is a photovoltaic application, you have a circuit.
Okay.
And your electron and hole will recombine not directly in the material where you excited, but electron will travel through one shoulder of circuit, hole through another shoulder of circuit, and they will recombine elsewhere on the heating element or the motor. So they will travel far and recombine far, non-radiatively. In the light emitting application, they are not, electron and hole do not travel through circuit. They recombine immediately at the same place, but with emitting of a photon. Right? So difference in photovoltaic and light emitting is that in photovoltaic recombination happens far and non-radiatively, and light emitting recombination happens locally, here with emission of photon through radiative process.
Okay.
but the trap state is enemy of both. Good?
Yeah. Enemy. Okay. So yeah. So I have these certain orbitals. I didn't include to which transition they are to, but this is the I guess the initial transition. So here we have excellent examples of where the entire molecule is active. So what this means is that an electron can be found in all these and not just localized in one area. It will be delocalized all over the material, compared to some of these smaller transitions that are not as ideal as these two, but still not just centered around in one area, more spread out throughout the material. So the cesium iodide rich surfaces are usually, yeah.
So I'm just wondering why your all bright LUMO are localized in very small area. Is it specific atom type or just
Excellent question. And
Yes.
several people were asking.
They were for some reason I noticed it. They're all localized around, usually around lead, the lead atom. So if you see like right here, I know it's a pretty bad example, but there's a bromide in front of the lead, and that's where the delocalization's at.
So the bromide just stays on our
Thing of
view,
Yeah.
but actually those looks like p orbitals on of the lead. It is what Alice was asking about projected dose, right?
I'm sorry for like trap states.
Someone was asking about p dose,
Yes, that was me.
and Daniel told that he declines to do p dose because she will give the same information via orbitals. And
But-
it looks like he's trying to address it right now.
Okay.
So your unoccupied orbitals are combined based on like p orbitals of lead,
Okay.
right?
Yeah.
Okay. So for 13 and above are unoccupied, and for 11 and below, were the charge density localized at?
in that occupied one?
Where are they localized at?
Yes,
Oh,
at which atoms? At
on
which?
the bromide atom.
So which color bromide is?
The pinkish ones. So you see like right here, right there. Yeah, they're just sort of everywhere. There's some too on the acetate ion,
But not much.
it's negligible. Like if you see, there's also this little graph right here that'll tell you the energy based on the diagram. So it's not perfectly scaled out, but you see there's a little hump, and that's just what this is contributing to. So it can be considered negligible.
So from this image, what is your main point? I mean, what is your main outcome?
My main outcome. So mostly the bromides are occupying the electrons, and well, the the leads are ready to accept.
Are there any other observations from here? If you look on the ligand, is there any contribution from ligands?
No, not hardly. I think there's some, just minor. For the most part, it's always just insignificant for the most part.
What do you think is it positive or negative side for your purpose?
It'd probably be a negative thing then, right? Because you sort of want orbitals on the ligands, or some type of delocalization on it.
No. It's if there will be no charge density on ligands, it is a really great result.
It's a really great result.
Yes, you want
Sounds
to.
good again.
It is a main result.
Yeah.
In some sense.
Okay.
But do you know why is main result why is
No.
so important thing?
No, that it's good to know though, but I'm kind of curious to know now. never was asked that.
So continuing question of Javed. Oh, Alice.
Yeah.
Oh, I'm very confused. How do you tell, like, from these specific figures, how do you tell whether or not it's the photovoltaic or the light emitting? Or how do you tell that in general? Like,
I guess he
Which
didn't
graphs?
say anything here.
which process?
I think I need to do a couple more calculations before I get up to that point. Is this
Okay.
just to see how the molecule reacts to where delocalization will occur and the probability of finding electrons.
Can I try to answer?
Yeah.
Yeah.
Well, if you, Daniel is studying fundamental properties of material.
Okay.
He's not building a device. If you would build a device specifically for target application, then you would add special functional groups. For example, as London is doing right now and Aaron did in the past, if you do photovoltaics, you intentionally add donor or acceptor compound on the surface. Right now it's surface only,
Okay.
with ligands just protecting the surface.
Oh, okay. So the only way you would know is if you had something else to
Yes.
like, got it.
So it's
Understood.
just fundamental study of the material with potential use for applications.
Okay.
But it is
That makes so
this
much
one
more
is
sense.
not a device.
Got it. Understood. Thank you.
So
Is
Oh.
Levi still here?
No, he went to the different meeting.
Okay.
can you explain why? You said why not having anything on the ligands is a good thing, or
Because ligand could create the dangling bond or it can create the localized bond. And it's very hard to control the ligand surface. So you use the ligand for passivating the surface only.
that's it. Okay.
So it is very susceptible to create the trap state most of the time.
So if you do see
Yeah.
charge density on the ligand, it
Yeah.
means you caught the trap state.
Trap state, yeah.
So trap state means charge density on ligands.
Okay.
So if you would show the orbital number 412,
Yeah.
HOMO, you would see that it is a trap state. You just, by some way, the presentation is set up that it doesn't show bad guys.
Yeah. So
It would be better if you show that orbital too, then you can differentiate why it's not bright.
Exactly, yes,
Why it's
yes.
bright, yeah.
okay. Yeah. Yeah. Gotta work on it.
So Jabet did ask very general question that has multiple answers. So his question was, what do you see on this figure? How do you interpret it, and what are main observations?
And that's why I'm asking any other observations
yes.
there.
There is an observation that Aaron would probably appreciate. Let's ask him his help. What do you see, what would you like on this images? How would you interpret it? Let's help Daniel.
Symmetry.
Charges inside the box. If you consider your perovskite,
Yes.
like your box and ligands, like the surface of your box. All your blue orbitals are on the inside. They don't leak out.
Can one? Yes, they do not leak out. Excellent. But can one interpret this box as a particle in the box? Are there any specifics about envelope function that can be seen by naked eye?
So like you can see nodes at like the top and bottom.
Let me show what I see here.
3, 2,
Well, when there are 3,
4, 11, and 403. I guess they have this.
just change color.
I think it look like envelope function, yeah.
So
Yeah, if you look on
when
the
density is localized on lens here, it is not yet lobes and nodes. One needs to do an envelope function that go along all of them. And there are only 3 layers, therefore this curve is represented only by 3 points. So here is again only 1 maximum. But if you go here, one can interpret it as envelope function does contain two maxima. So it is a ground state for harmonic oscillator, or not harmonic, for particle in the box, and this one is second harmonic. And same here, this one can be interpreted as one envelope function composed of these bromines, and here this n prime equals 1, n prime equals 2. So roughly, one needs to analyze it with carefully, but one can identify similarities with particle in the box. And it is not a big scientific discovery, but anyone who is reviewing your work would appreciate this analogy.
It can relate it to particle in a box as the analogy.
Mm-hmm. And it is kind of two separate boxes, one box for electrons and another box for holes.
Okay. Oh, that's good. Is there any more final questions on this or any observations? So here's a second model that I presented on. So the HOMO and LUMO gap. Yeah, we're just gonna yeah, we're not gonna talk about that right now.
You can just tell that it is a little smaller.
It's around 1.5. Okay, so it's a lower band gap than the other molecule has, the cesium iodide rich surface. But in this case, so the main giveaway right here is our gold or yellow. I'm colorblind, so it's kind of hard to see. So that surface right there is lead, bromine in that pattern. So same thing for the bottom one. So instead of using our baby blues at the surface, yeah.
Why these, bottom images look like different, is like kind of triangular shape?
It's probably the way I orientated, because it's compared to the other one where I did it, where I had it flat. This one was kind of the plane's going into you a little bit. It's sort of if you think about it in a circle, like 115 degrees.
And here you have used perspective view instead of orthographic.
Yeah, basically.
Perspective view from the top, maybe. Eh?
From
the
original angle.
Oh, okay.
I got it from the top one. I think I just flipped it to the side and whatever it laid on. I kind of got lazy and was just like, all right, it's on its side. So, or I think I tried 2 different approaches on this.
That
one.
could misinterpret your image. Yeah, so.
No, I think I tried a different approach on this second image instead of the first one, where I wanted to show this a little bit more instead of just giving you the flat perpendicular plane of view. That's just my one on that. But yeah, that's essentially it for these 2 surfaces. So density of states. So I guess the PDOS would tell me where what contributes to the conduction of valence bands. That be kind of helpful. But then again, I could talk about the orbitals, right? That's interesting. So yeah, same thing with the spectra. It's pretty much closely related to my other one, except that it's not as intense. It doesn't have as many peaks, but it's still found around the UV range instead of the R range, so lower wavelength. Same thing with transition energy. It's just if you like electron volts instead of wavelength, but so here we talk about orbitals. So with the with my lead iodide rich surface, I believe my HOMO was found to be about 347, and then my LUMO is 348 and above. So yeah, these are more delocalized all around the whole material, with many of the orbitals being able to find. You see some delocalization on the ligands on a couple of them. So yeah, it's not as active until we get on to the LUMO part, where most of our charges are on the bromide. So it's opposite of what we found out on the cesium iodide surface. On the cesium iodide surface, we found the HOMOs be able to, well, most of the charge being on the bromides. Well, in this case, it's flip-flop. But So, yeah, I think for the most part, this isn't as beneficial compared to the cesium-rich surface.
More orbitals with higher indices.
Yeah, so these are more closer. These are all more the HOMO ranges with
LUMO.
a lot LUMO. Yeah. So this. So right here we have pretty much more significant. Well, then again, probably not because I probably threw up the ISO values too hard on this one. But there is delocalization found on the ligands. And yes, this right here is an example of a trap state for the fact that it's delocalized in one area instead of spread out around the material. So if you always want to know what trap state looks like, this is an example where you see no delocalization on any other part of the material, just in one specific area. So same thing with yeah. Is there any questions on this? Yes.
It's not a question, it's just a suggestion. Maybe it would be helpful to make the orbitals, what is the word that I'm thinking of?
Transparent?
Yes. Yeah.
What was the word?
Transparent. So you can see through.
Oh, okay.
Yeah.
Yeah.
And just like blow them up a bit, maybe.
Okay.
Yeah.
Yeah, I could look into that as a course. Someday I didn't think about it too much.
What's the question here?
It was not a question, suggestion to make visually transparent.
Oh, I thought the question was the material is transparent or not. That's it.
No, no, not that one.
So conclusions: my cesium iodide surface is more favorable due to not being able to observe a trap state. Well, the ones I looked at.
Probably the rough they were just not shown.
I have to probably go back into that, double check that again. But for the ones that were most active, I didn't observe one. So, yeah, because a higher oscillator strength means the higher probability of that transition happening, correct?
And trap states have zero oscillator strengths or negligible.
They do have zero?
Yes, trap states,
Uh-huh.
they're trapped because they're not useful for optical activity.
Uh-huh.
They are in the list of oscillator strength transitions, but they have vanishing oscillator strengths. So if you select only those orbitals that contribute to oscillator strengths, you will never show trap states. You need to find something that is dark.
So basically, if I pick out any random transition that has a zero oscillator strength, most likely it will be a trap state?
Yes.
Okay. Alright. Yes.
So what is your next goal?
My next goal, so
You want to read in here, but
yeah,
I just
so hopefully I'll try to get my molecular dynamics and adiabatic coupling.
what do you need to do that?
Molecular dynamics, well, before I could do adiabatic, I need
No, I mean why you're doing these calculations. What's the purpose of
of this,
Which discoveries are you going to do
What are you
based
doing?
on non-adiabatic dynamics?
that? Yeah.
based off non-adiabatic, well, so from my opinion, from what I've learned about non-adiabatic coupling, it's basically isn't the pairing of electrons found in the conduction band, so the higher the coupling, the more probability that the electron will be found in the conduction band? Right? Because I
don't.
How does non-adiabatic dynamics relate to rates of cooling or rates of recombination?
Well, the higher the non-adiabatic coupling factor found to be, the higher the recombination time, or the faster.
You do not need to be specific.
Yeah.
You can tell that by exploring non-adiabatic dynamics, one can find rates of dynamical processes of cooling and recombination.
Okay.
That would be better if you third line in the goal
Instead.
instead of
Yeah, of course. Okay. Yeah. Be more scientific instead of a plain. Yeah. Of course.
I have one question on the previous slide. It's
Okay.
not a question, I'm just confused in whether. In the 353 image
Yeah.
orbitals,
Okay.
from the which direction you are showing this image?
The same direction, all of them. So, how I explain
Isn't
the
it, isn't it periodic in this, in the, what should I say? In the Z direction, in the X directions?
Yeah.
But if this layer and that layer is not look like, it's maybe because of how you're showing and in the X direction, I mean horizontal direction, is it periodic? It should be, I
Yeah.
guess, since it's the
Yeah.
same.
It's only on the z-axis. where-
But this age and this age is not look like periodic to me.
Write it down.
Yeah, so it's maybe because of how you're showing the image, then maybe that's why. I'm not sure yet.
Okay. Yeah. I'll look into that.
Let's thank Daniel. More questions?
On once.
No questions one, no questions two, no questions three. No questions, but thank Daniel once again. Tom, please, Daniel, it's your responsibility. Please collect feedback and then insert everything that everyone written into your slides. It could be a substantial amount. So previous talk did have like 10 slides. Next talk has 34 slides. And it is presented by Dr. Fatima. She is going to tell a story about her research of non-adiabatic dynamics. So please go forward. And Daniel may get some insight of what one can work with non-adiabatic dynamics. So the main specifics that a lot of us in this audience try to do non-adiabatic dynamics, but it is typically done in the neglection of the dispersion of so-called K points. And for periodic solids, it's not always good approximation. So Fatima is the first who tries to fight this obstacle. So it will be really innovative results.
Thank you.
And so please leave your feedback. Here are the printouts. And first slide is it's not actually the first. It is one of the very dense slide with equations, which is printed separately.
So today I'm going to talk about K-point resolved dynamics of silicon nanowires. Here is the outline of today's talk. First, I'm going to talk about context and challenge, and then which methodology was used for this research, and then research findings, and finally conclusions. So, silicon nanowire is a unique class of nanomaterial since it has intrinsic properties such as one-dimensionality, high surface to volume ratio, and silicon nanowires are applicable in solar cells, lasers. The electronic properties of silicon nanowires have been studied theoretically with different aspects such as doping effects, surface modifications, this kind of thing. But there is a gap remains in electron relaxation study for multiple K points. In our previous research, we studied electron hole dynamics of 3 different silicon nanowires for multiple K points, but momentum was conserved at that time. But the electronic structure of any periodic solid depends on K dispersion. Radiative and non-radiative transitions also depends on K dispersion. So in this research we study at electron dynamics. We didn't include whole electron dynamics of three different nanowires for multiple K points, and this time momentum is not conserved. So now I'm going to talk about the methodology. Molecular dynamics is a suitable approach to calculate on-the-fly electron to lattice couplings for semiconductors, and based on the density functional theory, a combination of rate field theory for electron relaxation and with on-the-fly coupling of electrons to lattice were used in this method. And here we can see the one electron Kohn-Sham equation, and this is the solution of this equation. Here we can see the wave function. This is, since the structure is periodic, one-dimensional periodic, since it is nanowire, so one-dimensional and periodic along z-axis. So this is the this is a periodic wave function, a block wave function, and G is the reciprocal lattice vector.
What is the dimension of the reciprocal lattice vector?
3.
No, in which units? I understand that it's three-dimensional, but in which units? Dimensionality in means of, is it like energy, time? What is the units of the G vector?
Angstrom.
Or inverse angstrom? Because you multiply G times R, and then you get dimensionless.
Okay, inverse distance.
Okay.
Since R is distance, yeah.
I have one question about the previous slide, actually not this slide. It's not a question, I don't know, that's why I'm asking. Is it K point, momentum can be changed in radiative transition? Or do we need to conserve? I hope I didn't look, well, I lied, I didn't, but I expect very much that through the slides there will be K point resolved radiative transitions as well. Oh, okay.
And here, this is the equation used for the calculating couplings between electron and lattice. And here we can see this wave function is, this I is the orbital index at K point, at K. And this is another wave function. J is orbital index, and this is different K point. Here you can see K is not equal J prime, and momentum is not conserved. Here, if we apply light pulse on model, then electron travels to excited state, then come back to the band edge LOMO. So when it comes back, it is non-radiative transition, so it passes some photons to the nuclear vibrational motion. Nuclei are vibrating because we applied heat, and there are and here we see the time interval between these two wave functions delta t. We are considering 1000 time steps. So when electron comes back to the band edge LOMO, it coupled with the nuclear motion. So basically the photon coupling.
Should it be delta T in the denominator for your couplings?
Yeah, here.
So the smaller, so that it looks like a derivative. Okay.
And this is the autocorrelation function that we can derive from couplings. And here we can see the rates of transitions. Those can be derived from, those can be get from Fourier transformation of the autocorrelation function.
Should the argument be if it is Fourier transform of like your, what is the argument of autocorrelation function?
Should be frequency.
Autocorrelation function. Tau is time, right? And upon you do
Omega.
Fourier transform, what is the argument of gamma? Should be frequency, right? Omega. Okay.
And those rates of transitions combine to make a rate field tensor. And time evolution of density matrix is here. And this term is for electronic energy dissipation, because when electron comes back to the band edge, it dissipates energy, I mean photon. And this is the term von Neumann term or something. This one, the first term on the right hand side. Okay, there was a question in my last presentation that how many K points was in my band structure, because I have shown this one last time, so there is no K points. There was no K points here since I selected.
I just had a fundamental question. So what is that 10011? I know it's like the way of how the shape is, but like, is there anything else other to that, like how it works, or?
Yeah, it's the so if silicon is crystal, right? So if you take bulk silicon and you can cut in different plane, right?
Okay.
Suppose along x-axis, along y, along z. So this is the cut of the plane.
So if it says 2 on the like last one, 211, so it's cut twice on the x-axis.
It's not x-axis, it's in the reciprocal. It should be the plane HKL,
Okay.
the reciprocal space.
Okay.
Which keyword one should look in Wikipedia to find it?
Brevis
Reciprocal space,
Or Miller?
Yeah,
Miller
Miller
indices.
Miller indices, yeah.
So take the inverse of that number, and that'll tell you in real space, like where it was cut. So 2 means it's cut right in the half.
Okay.
Like if it is 100, it grows, it propagates along x-axis. If it is 010, it propagates along y-axis. If it is 001, it propagates along z-axis.
Okay.
If it is 111, it means simultaneously propagates in equal measure along each of the 3 axes.
Okay.
So these are this was calculated for 16 K points, and I selected just a line instead of symbol. But here you can see symbols as but we are considering only 4 K points for these two nanowires and 3 K points for this one for our calculation.
Why?
Because for if we so our goal is to calculate the non-radiative lifetime of electron. For that we need to calculate rate field tensor and then electron relaxation rate. Yeah, in order to calculate rate field tensor, we need to consider all the coupling files. So for each an electron is traveling from one K point to the same K point, one K point to another K point. So there are 16 possibilities here. For each possibility, there are 900 coupling files. So 16 times 900. This many coupling files we have. If we consider more K points, then it will be expensive.
Too numerically expensive.
Yeah.
And also there are maybe another answer from this slide and previous slide.
Yeah, because if you look at this one, the shape pretty much same. So we can consider 4 because they are not deviated too much. They are in line.
Fatima, What's your x-axis or
X-axis,
on this diagram?
K point.
Oh, it's the K point.
yeah,
We can measure.
And what is the dimension of your x-axis? Units.
it's a nanometer, a distance, or vector.
Well, for each of your nanowires have different lengths and different values of momentum, but in each figure the range changes from 0 to 0.5. Can it be dimensionless? So like if your k vector, same as an introductory slide, if the dimension of your
Reciprocal.
reciprocal light is 1 over distance,
Distance.
and then
Oh,
you,
yeah.
if you convolute it with size
So
of the
it's
cell,
inverse
then it will
distance.
be dimensionless.
1 over r times r.
Yes, yes.
Okay,
So here it is
dimension.
dimensionless momentum.
Okay, here we can see the path of electron dynamics. So we can see electron can travel from this K point to this one, the same K points, or yeah, it can travel from one K point to another K point. So this is direct transition if the K points are same. This is direct transition if the K points are different than this indirect transitions. So in order to calculate the rate field tensor, we need to include both direct and indirect transitions.
And the main goal and main novelty that you try to investigate and deliver is the role of indirect transitions. Okay.
Yeah. So if we want to calculate rate field tensor in our local computer, we should have 3 kinds of files in that folder. Number 1, all coupling files, and it includes direct and indirect transitions, direct and indirect couplings, direct and indirect coupling files for direct and indirect transitions. All energy pop files, because I already mentioned that for these nanowire models, we considered more than 1 K points. So for each K point, there should be 1 energy pop file. If we consider 4 K points, then there should be 4 energy pop files. And this correlation code, you can see there are 2 names here. So they are involved in this building this code. I'm going to talk in details of coupling files now. So number 1, that folder should contain all coupling files, direct and indirect. Direct coupling files means couplings of orbitals at same K points. So suppose from K point 1 to K point 1, K point 2 to K point 2, K point 3, etc. And each for K point 1 to K point 1, there are 892 coupling files, and for K point 2 to K point 2, another 892. So there are 4 sets, yeah, and each set contains 892 coupling files. Now the indirect couplings, this coupling between orbitals at 2 different at 2 different K points. I'm sorry, these should be K points, and the form of the coupling file should be coupling dot K point 1 dot K point 2 and then the number. So each indirect transition should have 892 coupling files, and there are 12 sets here.
Huh? How many?
12.
Huh?
12.
How many sets?
12 sets.
12 sets?
And
So
then these are 4,
four
total
per
16.
And 16 is 4 times 4, right? So because you have,
Yeah.
it's matrix 4 by 4 from each K point to each K point. So there should be totally 16 sets.
Yeah.
Out
Polar
of them,
cells-
4 diagonal and 12 off diagonal.
Mm-hmm.
Okay.
So this is diagonal means the same K point.
Yes.
And that's why I'm telling that here for indirect transition 12 sets, for direct transition 4 sets, total 16.
Can I draw something?
Yeah, sure.
If you would present it to a new audience who never will see it for the first time, you,
It's a combination of 4 different K points. Not a permutation, it's a combination of 4 different K points. Okay?
Yeah, it's a 1 to 1, 2 to 2, 1 to 2, and then 2 to 1.
Mm. Yeah.
and then you can tell that there are 4 diagonals and 12 off diagonals for total. Right?
Mhm. And number 2 of all coupling files. So for silicon nanowire 100 and 111, there should be 4 energy profiles for 4 different K points. And for nanowire 211, there should be 3 energy profiles for 3 K points. And this is the format of the energy profile. This is these are the number of states, these are the energies of that state, corresponding states, and these are the number of electrons.
So the energies of orbitals of the same index will be different as you travel from one K point to
Yeah,
another.
exactly. Mm-hmm. And here is the code. So last time there was a question about this, this one and this one. So actually I took a snapshot only for a few parts, not, it is a big file. So it first it combines state field tensors for direct transitions. I mean here it like for diagonals. Diagonals, and then another for loop for these off diagonals, indirect transitions, and finally all of them are fed through a single supertensor. So it calls only this one, not this one. I didn't. This one contains all these 16 sets. And finally, once we have 16 states, then we feed all of them to a supertensor, this one. So we introduce 2 super indices, a big I and big J, and all of them are here. So the final form of the 5R file is, it contains like, so the matrix is R 1 1, so transition 1 from 1 K point to 1 K point, and then 1 to 2, and then 1 to 3, and 1 to 4. Then in the second row, 2 to 1, 2 to 2, 2 to 3, like this. 4 by 4 matrices, this one. 4 by 4 matrix, this one. Here we can see this 16 rate field tensors file we will have, and using the previous this code, we are getting this 5R file, and this is our final file. We use this one for electron dynamics calculation.
So this 5R file should be 6 times heavier than this triple R files, right? 16 times
heavier, yeah.
Okay.
Mm-hmm. And this is the energy profile. So for each nanowire, we have 4 energy profiles for 4 different K points, and there is a part on that correlation code, MATLAB code, So put all the energy states of all energy pop files in a single energy pop file, and there is this one. It contains energy states for all 4 energy pop files. And first it contains, it is orderly arranged. First k.1. Suppose if the energy pop file for k.1 contains 71 to 120 states, then this energy pop file will contain 71 for k.1 first, and then 71 for k.2, then 71 for k.3, 71 for k.4, then again 72 for k.1. This sequentially it contains the states. And here we can see that the 5 I didn't cover all the states here, just I selected some range 0 to 100 of these 5 are files that are final red filters of files. And so if I include the whole range, it will not be made. It will be still, it is not, I don't think it is like explainable or something. So I didn't include all of them. It's just
So can you please repeat what is the meaning of a super index? You did introduce it before, but just repeat it. In this diagrams, you have X and Y, or whatever, I and J. What is the meaning of this I and J? What does it label?
I and J, so I is for K point, one set of K points. So it contains.
Okay, keep going, discuss later.
So here if I go to, so here we can see this I is K point, number of K points here 1 to 4, since we have 4 K points. So 4 minus 1 times n states. N states means if we look at the energy pop file, the maximum number of states minus minimum number of states plus 1, that means the total number of states in energy pop files, that is n states. And I is the index, so you can index, we can see here 1 through n states, 1 through all the states in the energy pop file. So this is a big I, and this big J is another set of K points because it is indirect, right? So it will travel from one K point to another K point, not at the same K point.
So would it be right to say that one super index encodes 2 simple index, index of orbital and index of K point?
Yep.
So it is just 2 numbers encoded into one number that ranges in a larger range.
Yeah.
Okay.
Exactly. Okay. Once we have the super tensor 5R file and energy pop file, then we can put them in a single folder, and there is a MATLAB code for dynamics calculation. So all of them should be in a folder in local computer again, and if we run this MATLAB code, we should get electron, the rate of transition of electron. Here we can see the snapshot of this code. This is, this whole state is kind of messy. Since we are not interested to whole right now, we are only concentrated on electron states.
So there are probably some bug related to the PPP energies of course.
Yeah, for silicon 100 model, it works just fine for whole, but for the other 2 models, there is something I need to fix that.
Oh. IH, IE. It is not a number of orbital, it is super index. How do you select them?
Okay, so it is super index. As I said, in energy pop file, this final energy pop file. which contains like all of the states for 4 different energy profiles. I took the number from that final energy profiles, which contains energy profiles for 4 different K points, and this 65 is it is from
So you need to divide by 4 and find the and remove the rest of division. So what is 65 divided by 4?
16.
16 and 1.
17.
So it is orbital number 16, K point number 1. Am I right?
Orbital 16. No, I believe 17, then 1.
Huh? Like, what is the orbital number? Is it like LUMO plus 15, K point number 1? How to interpret your
Yeah, exactly. So
or whatever, HOMO minus 15. K
yeah,
point
so
number.
HOMO is first HOMO is for K.4, and then K.3 HOMO, and then K.2 HOMO, and then K.1, then again K.4, 3, 2, 1.
Okay, and IE equals 23. Which orbital and which K point is it?
So it is 4 orbitals LUMO plus
Wait. It's LUMO plus 5? K point number.
3.
Okay.
Yes. And
Does
then
it make sense or?
It would know before, just 4 in this
Huh?
case, because you have 4 K points.
Mm-hmm.
So if you had 3 K points, it would just be.
Divided by 3.
any question?
If you're not confident, if you do not believe this encoding, write down the comments for future improvements. At least there are a couple of people who believe that it's correct, but if you don't, write your concerns.
I guess, is there a reason that you numbered these this way, but you numbered like your super indices basically in a different way?
These numbers, you mean 65, 23?
Yeah, well, because the way that you numbered your super indices, you would be modding out by the total number of orbitals, and then taking the remainder to find out your. Oh wait, maybe that is the same. I don't know. Yeah, you can move on.
So I think I can
We
do
need to go through the whole screen, then it will make sense.
Yeah. Well, right. Yeah, it's really more
That's
just like a
fine,
technical
yeah,
question.
yeah.
I mean, it.
But it is critical. The whole code is based on this technical question. If you do errors here, the rest doesn't make sense.
Yeah, it would be numbered differently because in the way that you did your super indices, if you incremented by 1, you'd be incrementing by an orbital each time, and then you'd eventually loop to like the next K point, and then you'd loop through a bunch of orbitals again. Whereas this way, you go through K points, and then you move on to the next orbital, and then you loop through a few more K points, and then you move on to the orbital.
So the final energy profile looks like this one. So HOMO, this is for K.4. This energy is negative, right? Negative something. And the above on top of this is HOMO for K3, K.3, and this is for K.2, K.1. And this is for LUMO K.1, K.2, K.3. And it repeats. Does it make sense? So that's why this is a big number, 65. I can put here 1 to 20, because it is a big. It contains big number of states, so many states. And here is the thing. So here we can see in this video clip how electron travels from one K points to another K points.
Let's fix it. Do you know how to get back from making notes into maybe escape. Three. Yes.
So that's how electron travels from one K point to another K point. We can set another set of different set of.
Once again for us.
So what are your red dots?
K points.
And they're just plotted for the LUMO?
Let's play it once. Maybe. Do you know how to loop a movie so that it repeats again?
Yeah, it's a setting when it's up in like the top menu bar.
You need to put that in running.
Okay, next time you may do it, but let's play it once again and discuss. So this dots are changing.
Mm-hmm.
Is it distribution, like pointing which energy and which K point are mostly occupied at the specific instant of time? Aaron is, so he's interested in definition of these red spots, how to define them.
So these are the K points.
No, I mean, what is the red things?
So are they like charge density or occupation?
Yes.
Is it
density?
meaning positive charge? I mean, negative charge. Initially, it was like green color, right?
There was
Oh, no. Yeah. Oh, okay. So initially, the red dot was 1 on the top.
Right,
Then it distributed to the 3 different K points.
right. And then
So that means charge is relaxed to the 1 K point, 3 different K points.
why do they all have the same intensity though? Do they all have the same population?
That's another version.
It can be
Or is it-
degenerate. They're equally occupied.
So what is the red line doing then?
It's the path of transition. Electron. So this is just a one set of K points. We can set different K points here and.
Let me try to cooperate, and I can be wrong, but let me try to just put an equation right. So it is distribution of energy and K and T, so it changes with time. And it is summation over orbitals over K points. It is distribution like delta function of energy minus energy of orbital at given K point, bracket, times delta function of K minus K prime times occupation IK diagonal part of density matrix of time t. So if this orbital I and K point K are occupied at time t, then there is a block of density. Make sense?
And here we can see for silicon 100 nanowire model, these are the interested number of steps that I had used for calculating relaxation rate of electron.
So you're scanning through different initial states and record the rates of cooling.
Yeah.
as function of initial condition.
And for other two nanowire, also this. So, as
Do you have movies for all of the nanowires or only for one?
only for one.
Okay. Next time maybe for all of them to
Yeah.
see visually the difference. And this is what we have as a first slide, first printout.
This is.
So it is not visible on the
Yeah,
screen, but
I-
we may see it on the printout. So please guide us through. Click OK. Just maybe explain one example, one line or one cell in this table, and then
Suppose this one. Okay. Suppose for 100. So I feed there for 100 model. Here.
let me try to tell, and you will correct me if I'm wrong. So for each model, you're trying to develop a lot of data for rates as function of initial conditions. And for this set of data, you're trying to find fitting function.
Yeah.
Okay, and this fitting function is different for different nanowires and different key points, and therefore your fitting functions are look differently with different parameters.
Yeah. So if I go, so if we look at here, this K point 0.16, we can see here is the energy lens and the fitted functions. So for each K points, we can see the energy lens and which function was fit, which equation was using to fit this energy lens and the values of the parameters. This side is for direct transitions and this side for indirect transition. Yeah, so if I, it would be clear if I show you the next slide. Suppose, so this one is for 100.
Can you please run it to the full screen?
Sure.
So the symbols represent your numeric tables, and lines represent the functions, your fitting
The
functions.
Yeah.
Okay.
Okay. So as I showed earlier, the big table, the interstate number of states for which I calculated relaxation rate of electron. So this x-axis is the dissipated energy, and this is the natural logarithm of relaxation time for 10 number of states. Here we can see each set of data, like here the indirect transition for K point 0 and direct transition for K point 0. Those are same color but dark and light, so that we can see that at same K point direct and indirect transition happening. So for a 0, K point 0, this is the blue set of data, and this light blue is for indirect transition here. So we can see the first couple of points, this energy lens, it is fitted through a straight line, and this another one, another straight line. And for all of these K values, first couple of initial states follow the electron relaxation rate follow energy gap law, and after that number of initial states, electron relaxation rates follow inverse gap law. So those functions were written in the previous table. So this, the fitted function of this line and the parameters, intersection and slope. For this one, intersection and slope, the fitted equation was in the previous slide.
So you have for each color you have two lines, one for direct transitions only, and another for indirect transitions enabled.
Yeah, but those are dark and light colors.
And
Light colors are indirect.
The main result is as soon as you enable indirect transitions, your time on logarithmic scale becomes much shorter.
Yeah.
It shifts by orders of magnitude. So the effect of indirect is really drastic.
Because here we can see that indirect transition is quicker, because in indirect transition there are multiple pathways to relax from one K point to the ground state. That's why the indirect transitions are quicker than the direct ones for this nanowire. And these are the at different K points, the difference between indirect and direct transitions, and we can see there.
It's not times, it's logarithm of time.
Yeah.
So you need to
yeah, it should be logarithm of time actually.
Okay.
I have a simple question. So what's the meaning of energy gap for the indirect transitions?
Energy.
I
Energy gap law.
I have an answer. So it refers to initial conditions only. Energy difference between electron and hole at initial moment of time.
Okay.
Would you buy it?
Then there is no energy gap law, right? If there is only
It's not literally energy gap law, but it is the common concept that can be used as an auxiliary tool to analyze data.
And for these first 3 K points, this is pretty close, and this change is linear. And this is for nanowire 111, and these sets of data also fitted same way.
Just a second. I just suffer to see wrong units. And this trend of drastic difference by orders of magnitude holds for all nanowires.
For this one, as 111 and 100, but for this one, looks like direct transition is quicker than indirect. I don't know why.
Direct is quicker.
I don't know why.
We should not include it into the paper. Okay, interesting.
I don't know.
Okay, and what are your conclusions?
So, conclusions in silicon 100, the indirect transition is quicker because indirect transition is quicker than direct transition, and the difference is almost constant for 3 K points except the 0.5, and it changes, the difference changes linearly.
Fatima, what is gap law?
Gap law, so electron relaxes quicker if the energy difference between the states is relatively closer. I mean, like an electron relaxes from one state to another if the energies of these states are close. I mean, you know what I mean? If the energy difference is big, then it will not relax quickly.
So as a curve, what would it look like?
Let me translate into chemical language. If the activation barrier is 0, reaction is quicker.
Okay.
Yeah, activation barrier is here the energy difference. So if simply if electron wants to relaxes from the higher state to the low mode, then it will take time compared to if electron relaxes from the lower state, like suppose LUMO plus 1 to LUMO.
So in some sense it is declaration of resonance condition. If they're in resonance, then it is instantaneous. If they're off resonant, it's slower and slower.
And so in indirect transition, electron gets additional pathways to relax. That's why the relaxation is faster. And for almost all k values, for in first couple of initial states, relaxation rate follows gap law, and after that relaxation rate follows inverse gap law. And almost the same thing for silicon 111. Indirect transition is quicker than direct transition because there are additional pathways to relax. And for k values, there are two regions. First region in first region, electron follows the relaxation rate follows the gap law, and then after that relaxation rates follow inverse gap law. For silicon 211, direct transition is quicker than indirect transition. I don't know why it's pretty strange, but and a gap law for the initial couple of condition states, relaxation rate follows gap law, and this is the same for all the nanowires. And finally, acknowledgements, Dr. John Vogel, Yolon Han. I want to thank Aaron. He's very helpful. And then thanks.
Okay, then thanks, Fatima. Someone has Jared.
Yeah.
I feel like I'm just. Are there more questions to Fatima? Or everyone is satisfied?
Sort of related. So if you were an experimentalist and you wanted to observe an indirect transition, how would you, or what experiment would you use?
Transition.
And indirect, like a phonon-assisted, non-radiative relaxation. If you're going to put this in a paper, that's probably something someone would bring up. You'd have to do some sort of femtosecond.
Spectroscopy.
Maybe. Or you'd have to be able to like measure like phonon modes. Because if you do an indirect transition, that's going to activate some mode somewhere. I'm not sure exactly how you would measure it, but that's what you'd look for.
Any ideas?
There's some spectroscopy.
Yeah, which spectroscopy?
Obviously not scanning. Oh, that's microscopy.
No, spectroscopy. I have an idea. It's one of the most expensive spectroscopic equipment. You may want to do 4-wave mixing or 3-pulse photon echo. When you have 3 lasers at different angles, you stand away, submit your pulse, and then the signal will go into the 4th direction. And by changing relative angles of the incident lights, you establish the relations for the k vector of the outcoming pulse. So, and
Does it depend you have to change angles because it's like reciprocal?
Yes. So it is, you can determine the momentum of a photon. And then and then through conservation law, it will indirectly affect the momentum of electronic degrees of freedom, and then it will emit a photon.
You are the
again.
only participant in the conference.
Thank you. And it can be related, one can establish this connection. So it should be possible, but very not easy.
Have to make better friends.
Yeah. More questions? No. Huh?
I have a question.
Yes, please.
Because before I have the impression that the simulation for a very large cell with just gamma point is basically the same as very small cell with multiple key points.
Yes.
So it seems after this work, so it is not necessarily true.
In order to prove it, Fatima may want to enlarge her simulation cells 4 times and check if the rates will stay the same. But for some models of practical interest, super huge cells cannot be possible because even unit cell is already big. And it was always interest of community, like is there a chance to change the value of momentum during the relaxation? So even if it would have no practical implementation, it would answer a lot of curiosity questions. Okay. If not, thank Fatima once again. And please collect feedback from everyone.
Yeah.
So London volunteered to present this Friday. What will be the topic?
Essentially the same thing that I'm doing, except it's like a methyl ammonium lead iodide perovskite. And if I remember correctly, it's an anatase titanium dioxide. So it's not quantum dots, it's like a 2D film.
Okay, and who are the authors?
I can't remember.
Oh, it's a literature
Yeah.
presentation.
You recognize the one guy's name because he does